Good afternoon. So let me start with the usual request of questions, if you have things that are unclear until now. So everything is simple enough. Yes or not? You hesitate. Too many things are unclear and you don't even start. So next week we'll try to organize one slot to see the problems, okay? And hopefully by that time you will tell me what are the unclear things. Okay, so let us start a new chapter today, which has to do with symmetries. Symmetry in quantum mechanics, very elementary treatment, okay? And the first thing that I need to remind you is very elementary linear algebra concepts regarding space transformations of just vectors, okay? Ordinary vectors on the plane or in space, okay? Say in space. So the first obvious, I will draw things mostly in 2D or even 1D sometime, okay? But you should imagine everything in more general cases. If you have a certain vector, okay, call it R, you know that you can translate by a certain A, obtaining a new vector R prime, okay? So every vector, every point in space is translated by the same amount A. And this is just a very simple transformation which brings R into R prime equal to R plus A, okay? It's called translation, okay? To remind you that A is what determines the thing, I will write this as T of A. It's a linear, very simple linear type of transformation. Strictly speaking, the mathematician wouldn't call it linear because linear operators are those that send 0 into 0, okay? But you understand what I mean. Okay, another very simple operation is the rotations, okay? Let me illustrate it in just 2 dimensions. So I will rotate everything on an axis that is z, pointing towards u. And if I have a certain vector, r, a rotation by a certain angle, theta, will bring it into a new vector r prime. Okay? And you know the relationship between r prime and r. So this would be a transformation bringing r into r prime. And you know that r prime is related to r by a rotation matrix. Okay? So this time I should write r applied to the vector, where r is generally parameterized by, you have to tell me 2 quantities. One, for instance, is the angle, and the other is the axis over which you rotate. For instance, in this case would be the z-axis, okay? So this would be rotation by theta around z, okay? So once again, to remind us that this is specified by this particular thing, I will write this as r of theta and z, okay? Now, example, for this thing that I have drawn here, r is just the very known object minus sine theta 0, 0, 1. Okay? Is this clear to everybody? So z is not touched, and x and y are touched by cos theta minus sine theta. So for instance, the x vector, unit vector, is shifted into cos sine, is rotated into cos sine. The y is rotated into minus sine cos. Okay? So this is the way to just determine which are the columns of this. And notice that, well, these matrices have the property that the transpose is equal to the inverse. Okay? The inverse is obviously a rotation by minus theta. And you see that if you rotate theta into minus theta, this doesn't change, but this changes sign, exactly like if you transpose. Okay? So this is. And another property is that the determinant of those matrices is always plus 1. You can calculate, it's very easy. It's cos square plus sine square is 1. This is true for any rotation, in fact. Okay? There is one more important space transformation that is so-called inversion. Okay, so the inversion is simply the following operator. Let me, in fact, call it just E. It sends R into minus R. Okay? So if I had to draw in 2 dimensions, it would send R here into every R into minus itself. Okay? And you realize that, in fact, in 2 dimensions, this is not a new transformation. It's simply a rotation by pi. Okay? However, if you visualize this in 3 dimensions, you realize that you cannot reproduce by rotations. Okay? The matrix representing this in 3 dimensions is minus 1, minus 1, minus 1, and 0 everywhere else. Okay? So the determinant of this matrix is minus 1. And you realize that every rotation has a determinant plus 1. And if you multiply several rotations, the determinant is the product of the rotation, so always plus 1. And you can never get minus 1. Okay? In 2 dimensions is spatial in some sense, because in 2 dimensions the inversion is just minus 1, which is exactly this matrix for theta equal to pi. Okay? So it's a very special case. But in general, inversion is a new object. Okay? So is this clear enough? This is very, very simple, I guess. But what, in principle, I can do is to do the following. From now on, I will indicate by R a rotation possibly followed by an inversion. Okay? So R for me now is either just a pure rotation or R times inversion. Okay? These are called proper rotation. Okay? And these are called improper rotation. Okay? Though the difference is that this has determinant equal to plus 1, and this has determinant equal to minus 1. Okay? So I will unify both into just one thing. And therefore, if I put everything together, the most general transformation that I have written for you until now should be specified by R and by A, okay, and sends any vector into the rotation of the vector plus possibly a translation A. Okay? So you combine both. You first rotate and possibly invert and then translate. All right. These are called just roto translations for obvious reason. Okay. Now, obviously, you can combine things. Okay, you can make products of several rotations, several translations, and you will find quite easily to prove that these operations form a group. Okay, they form a group. Now, I will not go into the details of the few properties that we have to show to prove that something forms a group. There must be an identity, which is obvious, just no rotation, identity in rotation and zero translation, okay? There must be a composition rule, okay? How do you compose two things? So for instance, I first do a rotation 1 with a translation by A1, and then I want to do a rotation 2, followed by a translation by A2, okay? What happens to a vector R? Let's see. The first sends R into R1, R plus A1, okay? When I then apply the second, it sends this vector into R2, the vector, plus A2. Is this clear? I've just applied twice the operation. The first and then the second applied to the new vector. Okay? So you see immediately that this is nothing but the product of the two rotations applied to R plus a translation. However, the translation is not just the sum of the two, is the rotated of the first plus the second. Okay? So this is a new translation, but all in all, this is nothing but a rotation by R2, R1, and a translation which is given by this vector. Okay? Is this clear? So the composition of two rotor translation is a new rotor translation with given things. Is this clear? So this is the composition, and you can prove that there is an inverse and so on and so forth. Okay? Now, all this is just operations, linear operators on vectors, but we have to look what these concepts imply on functions, on wave functions, okay, on states of our system. So, for instance, let us ask ourselves what happens to a function, a wave function, if I do, for instance, a translation. Okay? Well, let me draw this thing in one dimension to make things. So this is my function, psi of x. Okay? Suppose. And suppose that I want to translate this function. Okay? So what will happen is that this function, for instance, by a certain amount a, this function will become something like this. Okay. Well, it's not perfect, but you understand. Okay. So every point is translated by a. Okay. What function is this? Okay. So this is a new function, right? This is a function psi prime of x. Can you tell me what function is it? So at any given position, okay, the value of the function is equal to, so psi prime of x at any given x has the same value as psi at x minus a. Okay? It's important. I translated the function by plus a, for instance, in this case. Nevertheless, the new point where I have to evaluate the function in order to get the new function at x is the translated back point. So in some sense, I will define now this psi prime to be the transformation of psi with the translation Ta. Okay? Is this clear? This is now, notice. Let me see what I do. Okay. This is a new function, okay, which is obtained by acting on with this operator, which is P of Ta. I indicate this way because I don't want to confuse it really with TA. TA operates on vectors, okay, on points. P of TA operates on functions. So takes a function psi and brings it into a new function, okay, which, however, is very simple. It's just the old function at the translated back point, okay? So let me rewrite this in a better form. Oops, this thing is too wet. I write it here. So P of TA acting on a function psi is a new function which is equal to psi calculated at t to the minus 1 of a applied to x. Okay? You see, this x minus a is the inverse of the translation I have operated here. Okay? I might write it as t of minus a, but perhaps it's better to understand that this is really the inverse. In a rotation in general, is the inverse rotation. Okay? All right. Is this clear to everybody? It takes a little bit to be, I mean, to not to confuse where I operate. Okay? So t, we agree it operates on points. Okay? So when I write t of a of x, it means x plus a. T to the minus 1 of a of x means x minus a, this. Okay? P of t operates on psi and gives me this new function. Okay? All right. Now, you might be worried about what operator is this? Have we already seen it? Maybe. Well, it doesn't look like. But I will show you that indeed we have. Okay? So let us be a little bit more explicit on this function here. So I rewrite again as psi of x minus a. And now I assume that psi is infinitely differentiable, obviously, as we will always assume, essentially. Then this is what? Is psi of x, okay, minus a, the derivative of psi, calculated for, I mean, in x. Then there is a plus a square over 2 factorial, the second derivative of psi, minus a cube over 3 factorial, the third derivative of psi. Okay? I'm doing a Taylor expansion. Close to, obviously, x, okay, expanding in a. Now I want to understand what this is. Well, the gradient, I know what it is. This object here. Let's see. What is it? Have we ever seen this? The momentum. Okay, so this we recognize. This is minus I A, the momentum operator, divided by h bar. Okay? You see the momentum has a minus I times minus I gives me the minus. The A is there. The h bar cancels whatever is in the momentum. Okay? So this is the momentum operator applied to psi. And it takes very little to realize that this is 1 over 2 factorial minus IAP over h bar applied twice. Right? You get just a square, then you get the second derivative, okay, and then you have the 2 factorial. And similarly here, you have 1 over 3 factorial minus IAP over h bar applied 3 times, okay? So all in all, this is the identity, on the contrary, applied to psi. What do we have here? Huh? This is nothing but, in a disguise, e to the minus IA, the momentum operator over h bar, applied to psi. Okay? So you see this operator here, P of t, which represents the translation when acting on the functions, is nothing but the exponential of the momentum operator. All right? Is this clear to everybody? You can prove this in pretty general form. So if this is a function in 3 dimensions, and this is a vector in 3 dimensions, then the result would be generalized. Let me skip the intermediate thing as follows. Okay? A dot P. Notice that Px, Py, and Pz commute. Therefore, these 3 things you can equivalently write as e to the minus I ax Px, e to the minus I ay Py, e to the minus I az Pz. Okay? Because they commute. And so, therefore, you can split the exponential into just the product of the 3. In other words, you can do the translations the way you want. You first translate in x, then in y, then in z, okay, or vice versa. Doesn't matter. They all commute, and therefore there's no problem. All right? No, in fact, that will be the next thing. One comment before we go to rotations is the following. You see, in some sense, if A was infinitesimal, I would just truncate this perhaps to the first linear term. Okay? And you see that a finite rotation is just the exponentiation of this object. Okay? So just square, cube, and things coming from the exponential. Next thing, you see the analogy with the Hamiltonian and the unitary evolution operator. Let me erase what? Well, I write here. If you remember, we said the state at time t is equal to e to the minus I h t over h bar, the state at time 0. Okay? And you see immediately that this is basically the same. Okay? This is nothing but the translation by A, while here I have a translation in time by t, okay? So in some sense, this is essentially the same thing, okay? Because, okay, do you see the strong similarity? So as the Hamiltonian performs translation in time, the momentum performs translation in space. They're pretty much similar. There is a slight asymmetry in non-relativistic quantum mechanics, however, between time and x, because you realize that time appears in the Schrödinger equation with the first derivative, while, for instance, x in the Laplacian appears as a second derivative. X is an operator which commutes with p, while t is really, I mean, not an operator. It's a continuous parameter that. So it's not a total thing, but it's a very suggestive similarity. Yep.
Can we go back using the time translation operator? Can we go back and forth this time?
Oh yeah. Yeah. If you multiply by e to the I plus, okay, e to the I, okay. So if you put e to the I t over h bar in front of this, this must be equal to e to the I h t psi of t, and therefore this is the unity because you can sum the thing. So psi of 0 is this operator applied to psi of t. So
yeah, mathematically this works, but is it physically acceptable?
well, in principle, yes. I mean, physically the equation admit you can propagate back. There's no problem. Then there's another question regarding the error of time. But quantum mechanics at this level is totally reversible. Okay? Obviously, you know that there is some form of irreversibility in actual macroscopic systems. Okay? However, at this level, at least as far as the Schrödinger evolution, everything is perfectly time reversible. Okay. Now, the discussion about rotations that are written here goes along very similar lines with a few differences, however, because rotations, unlike translations, do not commute with each other. You know this very well, okay? If you take an object and you first rotate around, say, z and then around x, or do the opposite, the object will not end up in the same position, okay? So rotations do not commute among each other, okay? While translations do. This makes the discussion slightly more complicated. Nevertheless, the basic structure is the same. So let me just hint for you what you do for translation. So I write here the thing that we have proved. P of TA of psi is just equal to e to the minus I a p over h bar psi x. Okay. Now, if I have a rotation, so here I should imagine now a function in, say, in 3 dimensions, whatever, and I rotate the function, okay? Question is, what is the p associated to this rotation? For instance, let us rotate around z, okay, the thing that we have there, around z by an angle theta, a certain function, and let us ask ourselves what will be this function. You realize that the function at a certain point is equal to the function before at the rotated back point. Again, same argument, okay? So this function will be just a function calculated not at x, but at r to the minus 1 x, okay? Is this clear? But r to the minus 1 x is what? R to the minus 1 is this, okay? So r to the minus 1 x means you have to apply the vector x, y, and z here, okay? I write x vector, but then if I have to write the coordinate, I write x, y, and z, okay? So it's very simple to calculate this object. First component is x cos theta plus y sine theta. The second component is minus x sine theta plus y cos theta. And the third component is untouched, it's z. Okay? So this is the new 3 variables. Okay? So I should think of this as a function of x, y, and z. And this is telling me that this function of x and y and z is equal to psi of x cos theta plus y sine theta. Second is minus x sine theta plus y cos theta z. Okay? In full detail. Clear? Very good. Now, let us try to do what we did for the translation. There, remember, we had psi of x minus a, and we expanded. Now we have a function of theta, and we have to expand this. Okay? Now, in fact, let me write this object as x plus some delta x. Okay? And this as y plus some delta y. How do I get delta x and delta y? Well, nothing could be simpler. Delta x is simply equal to x times cos theta minus 1, right, plus y sine theta, while delta y is equal to y times cos theta minus 1 minus x sine theta. Okay? Is this clear to everybody? Just rereading what must be delta x and delta y. Why I do that? Because in this way I know that I'm calculating something. You see, when theta is small, this is small, this is small, this is small, this is small. So these two quantities are small. Now, I calculate, therefore, an expansion in delta x and delta y. And this expansion starts with psi of x, the function at the point x, y, and z, plus. Then I have to calculate the derivative of psi with respect to x times delta x, plus the derivative of psi times delta z, delta y times delta y. There is no derivative in z, okay, so I just don't write it. Then I would have other terms, obviously, so second derivative times delta x squared plus second derivative times, plus mixed terms, okay? So other things, which I don't even write, but you know that they should be there. Let us calculate this first. Now, suppose that theta is small, okay? So if theta is small, this quantity here is equal to linear order in theta. It is just equal to y times theta, okay? Plus things that are of order theta squared. This quantity here, still to linear order in theta, is equal to minus x times theta plus order theta squared. Notice a different sign due to the rotations. And then if I write this, I have psi of x plus. So delta x is just theta times y d in dx of psi. And then this is minus x times the same theta d in dy of psi. Okay? Plus, okay? Plus things of order theta squared. Clear? Yeah.
Here we switch y and dy dx since they commute, right? In general, this is not true.
Sure, these are just numbers. These are just numbers. No, by the way, they commute even as operators. I can write the y. I mean, this is a number, okay? The operator really acts on the function only, not on this. So in any case, I should better write this as delta x and delta y, okay? Just to be precise. So there is no really ambiguity where delta x should go. But I mean, even if you now get the things wrong and you try to put y here, there is no difference because y and the dx just commute, okay? But in any case, let's put it before where it stands, okay? Now you start seeing things, right? This is let me write as, let's see. Let's write minus I theta over h bar times the LZ. What is it? So this would be minus I theta over h bar x py minus y px. And this is, in turn, minus I. There is a minus I h bar coming from here, so I put here minus I h bar. And then I have x d in dy minus y d in dx. Okay? So if I get rid of this thing, this is minus theta and that's it, right? Minus theta x dy, or let me change sign, so plus theta y dx minus x dy. Okay? So you see that this is exactly what appears here. So this operator here is nothing but very similar to what we did for translation, minus I, the parameter that performs the infinitesimal, in this case, rotation, over h bar times the appropriate momentum. In this case, the angular momentum is associated to the rotation rather than the linear momentum. And you see it is the angular momentum around z, the axis I am rotating about. You realize that a very similar thing would be if I rotate around y or around x. Okay, very, very similar. It is also quite suggestive that if I sum all these things, okay, to all orders, I should obtain something like e to the minus I theta over h bar Lz applied to psi. This is very reasonable in some sense, right? However, you realize how more complicated it is to show really the equality by doing derivatives, because you have, first of all, functions of two variables at least, because one is fixed. Then I have to take all the second derivatives with the mixed term, all the third derivatives with all possible mixed term. And I should sum them and see that this is really the expansion of the exponential. If you do it directly, I guarantee, I think it's pretty much boring and not particularly illuminating. So I now want to show you a proof of this thing, which involves actually a trick that is often used in many, many contexts, similar contexts, and therefore I think it's in general useful to know. So in order to do things better, as is quite common in physics, mathematics helps, okay? So you do a little bit more of mathematics understanding and you realize that something is very, very simple. While a direct approach might be very cumbersome. So let us do a little bit of the mathematics that we need to do this problem. So first of all, some general properties of these objects that we have discussed so far. I told you, if I have a certain operation T, any roto translation, whatever, there is a P of T, which I can define, acting on the psi, such that if I calculate, sometimes in the note I use R, okay, x would be the same. If I calculate the transform function at x, this is nothing but the function at the transformed back point. Okay? This is very general for any space transformation T. Now, one thing that you can prove is that, in fact, these objects now, the P of T, form a group. Exactly as the T form a group. And you might ask, what is the composition? Well, I mean, it's pretty simple. You see, if I do a first transformation, means calculating psi, then I can do a second, okay? So, for instance, if I apply P of T2 after having applied a P of T1, sorry, okay? So to a function, and I calculate the result in x. The first one amounts to calculating psi at position T1 to the minus 1, okay? But then I have to apply still the second. The second means calculating the same psi at T2 to the minus 1, T1 to the minus 1 of x. Okay? So I have to apply the two inverse transformation in a certain in a certain thing. But you know that the inverse in this way is equal to T1, T2 inverse. Okay? You know that the inverse of a product is the product of the inverse in the opposite order. Okay? So you see immediately that this product of two operations on the psi is really a P of T1, T2. Okay? So notice the opposite order, okay? But apart from that, it's a very simple thing, okay? So they form a group. You can compose them.
Do they have a name?
John. The name of what? It's the group of, it's a group of transformation. For the time being, it's a group of transformation. In a second, I will give you a name for the, when we will specialize to the group of transformation that leave the Hamiltonian invariant, okay? Then that is called the invariance group of the Hamiltonian. But this is a group of transformation. Now, they are not only a group. Each transformation is unitary, okay? A unitary operation is a bit like this, okay? So it's something that doesn't change the norm of a vector, okay? So to be more specific, a unitary operation, if we have two vectors, psi1 and psi2, and you apply a unitary operation to both, then the norm doesn't change, which means it's a bit like when you rotate, for instance, both things, the scalar product would be unchanged, okay? So rotations, you realize in ordinary things are the analog of unitary. They are called orthogonal in that case, transformation. Okay, now you realize that this implies that if you bring this, for instance, here, okay, and you know that it becomes the Hermitian conjugate, this is telling you that psi2 Hermitian conjugate of u times u psi1 is equal to psi2 psi1 for any pair of psi2 psi1, okay? Which means that this object here has to be 1, okay? So which also means that u dagger is exactly equal to the inverse, okay? So unitary operators are operators whose Hermitian conjugate is equal to the inverse. They shouldn't be confused with the Hermitian operator, where the Hermitian conjugate is equal to the operator itself, all right? It's the inverse. It's a bit like the rotations. I wrote before that for the rotation, the transpose is equal to the inverse, okay? Now, rather than the transpose, you have to take the Hermitian conjugate, which is transpose and star for matrices would be. Okay? Very good. So let us prove that this P of t are all unitary. Okay? This is very simple. Let us calculate directly Pt of a certain function psi2, for instance, Pt psi1. What does it mean? It means an integral in dx. And then I have a function here that is Pt of psi1, which means psi1 calculated at point t to the minus 1 x. Okay? And here I have psi2 star calculated at point t to the minus 1 x. Okay? Now, on the contrary, psi2 psi1, which is what I want to prove that these are equal, would be almost the same integral, but without the t to the minus 1 there. Okay? So this is psi 2, psi 1. Clear? Now, you see the two differ simply because here in this integral, I have points t to the minus 1x, t to the minus 1x rather than x and x. But you realize very easily that these transformations are just rotations and translations, okay? But I am still integrating over all space. So you can change variable from here to here, and the Jacobian of this translation is 1, because the rotations have a determinant which is 1. The translation are very, very simple when you take derivatives, okay? So the change of coordinates from here to here has a Jacobian exactly equal to 1, which means that you can freely do this, okay? In other words, integrating with respect to this new variable, you could write this as follows. Call this the new variable, and in the new variable, the integral is exactly identical. And this proves immediately that PT are unitary. Okay? Good. So armed with this little mathematics, that the PT are a group of unitary operators, we can do this proof in a much simpler way. Oh, by the way, you see immediately why these operators are unitary. LZ and P are Hermitian, okay? So prove that if you calculate the Hermitian conjugate of this, due to this I, you get a plus, okay? And if you multiply, then obviously plus and minus cancel, and you get unity. Okay? So it's a very simple thing to actually verify that they are indeed unitary from the way they look. Now, in order to prove this, I will use this device. I will write a differential equation for the P, okay? And I will show to you that the solution of that differential equation is indeed this, okay? So you see, it's rather than expanding to all orders, I will use a kind of smart shortcut. Let us see how to put this thing. If I rotate by an angle theta plus a small angle epsilon around z, okay? What I can write? I can write that the rotation by theta plus epsilon around z is equal to the rotation, for instance, by theta preceded by a rotation by epsilon, or vice versa, since rotation around the same angle commute, I can also rewrite this as r of epsilon z, r of theta z. Okay? Is this clear? The rotations you can just decompose into first theta and then epsilon, or vice versa. Now, we said PT are a group which, in fact, you see, inherits, in some sense, the same type of properties that the transformation have, okay? So if I have to write, for instance, what is P of R theta plus epsilon, okay, I realize immediately that this is nothing but P of R epsilon z times P of R theta z, okay? Just because of this and because of this property, the same property is inherited by the P, okay? So you can perform rotation by theta, then rotation by epsilon, and this is equivalent to a rotation by theta plus epsilon, okay? Now, let us write this object now, knowing that this is infinitesimal. Epsilon is infinitesimal, which means that this object is what we just have calculated. All you have to do is to remember that now I am really assuming epsilon to be small. Okay? So, well, in fact, this I don't know, so forget about it. I wish to prove that. Okay? So, but if epsilon is infinitesimal, I can really stop here. Okay? So I write this as identity minus I epsilon over h bar Lz plus things of order epsilon square applied to P of R and theta. Is this clear? No. Where did you lose me? Here? Here? Okay. Now, if I have a rotation by an angle that is, say, 37 plus a little bit around z, this must be totally equivalent to a product, the successive rotation by an angle of 37, followed by a rotation of a little bit, right? This is what this is telling you. It's telling you that the rotation by 37 plus a little bit is rotation by 37 followed by a rotation by a little bit. Or vice versa. You first rotate a little bit and then you rotate by theta. If you want to verify it, it's not very difficult. I mean, in principle, you have to write this object here. You have cos of theta plus epsilon minus sine of theta plus epsilon, blah, 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 blah. You have to use addition formula for the cosine, and you will actually realize that this is true. Okay? It's physically very, very reasonable. If you want to verify mathematically with the matrices, it takes a little bit of trigonometry, and there it comes. Okay? So if you start from here, and you realize that the p, when you multiply them, don't do nothing but essentially what the t do. Okay? So for instance, from this object here, to be really fully explicit, let us prove a few of these things. For instance, if I want this object, the product of two, this one, P of R epsilon, P of R theta, what this object is telling me is that this is equal to P of the product of the two in opposite order. So P of R theta z, R epsilon z. But I know that this is nothing but, where is it? R of theta plus epsilon. Okay? So this is P of R of theta plus epsilon. And that's it. This is what I used. You see? Okay? So I wrote here that P of theta plus epsilon is equal to the product of the 2P. Exactly as the rotation do product of the two things. So they just mirror in some sense. In fact, they're called a representation of this object. Okay? Just if you do theory of representation of groups, you will discover that this is a representation of this group, because they kind of mimic. Is a perfect one-to-one correspondence of what the group does on the vectors, they do on the functions. Okay, now, if this is clear, okay, so if this P of R theta plus epsilon written in this way is clear, now let us do one more step and try to write, let us try to write the derivative of P of R and theta with respect to theta. How do you define derivatives? Well, you define derivatives in the usual way. You say, okay, I have a P of R theta plus epsilon minus P of R and theta, and then I divide by epsilon, and I take the limit epsilon going to 0. This is, any meaningful derivative should be like that, right? Okay, now, this I know. I have calculated here. Okay, so it's equal to the limit, epsilon going to 0, of P from the identity of R theta Z minus I epsilon over H bar LZ times P of R theta and Z, okay, minus P of R theta and Z divided by epsilon. In principle, here I have other terms, plus order epsilon square, okay, which I didn't write. They're here. However, you notice that this and this goes. This and this cancels, but these are higher order than epsilon, so when I take the limit, don't count, okay? So the limit is actually exactly given by minus I over H bar LZ times P of R theta and Z, okay? So the derivative with respect to the parameter theta of this operator here must be equal to this object times the same operator. And now you realize also that when the angle is 0, if the angle is 0, this must be the identity. What is an operator such that for theta equals 0 is equal to the identity, and if you take a derivative with respect to theta, you bring down minus I over H bar LZ? Must be this, right? Okay? Now, this is a proof, mathematical proof, which you see uses, however, group properties and writes a differential equation. It's a very simple thing. So once you know the infinitesimal action of an operator, then you can essentially, through this differential equation, reconstruct the full solution by exponentiating. This is a very useful trick, and people who do Lie algebras and Lie groups, they use it all the time, okay? So in fact, this is called the Lie. L is said to be the generator of the group, in the sense that if you take the exponential of it, you get the group. All right. Now, I'm not going to prove this for you, but you realize that much of what I said focused on Z, which is, however, very much arbitrary. And you understand that if rather than rotating around Z, I was rotating around some direction n in space by an angle theta, I should expect that e to the minus I theta n dot L over H bar, so the projection of the angular momentum operator on n should represent the generator of the rotation around this angle, okay? So I expect, and indeed one can prove, that this is just the rotation around theta around n, okay? So this generalizes my previous formula. When n is equal to z, this is just Lz, but in general, it's a combination of Lx and y and Lz, depending on where n is. I should warn you, however, don't think of writing this as an xlx plus ny ly plus nz lz and then splitting them, okay? The first step is correct. You can write it as a sum, but you cannot split this as three exponentials because they do not commute, Lx and y and Lz, okay? And this is due to the fact that three rotations around x, y, and z cannot be freely put in any order, because otherwise you don't get what you think you are getting, okay? To be more advanced in this game, one should introduce a way of, for instance, parameterizing any arbitrary rotation with three angles. And there is a very useful parameterization that is called the Euler angles parameterization, but it requires some careful drawing. And in any case, we will not use it in any way. So unless we use it, I would not spend too much time on this. There is a way of parameterizing the rotations in such a way that you can really view it as 3 successive rotations around the 3 orthogonal axes by appropriate angles, which are, however, given by the Euler angles and not just an x and y and LZ. Okay. Is this clear? Okay. So until now, I've talked about transformation in space and their image on operators in functions that are essentially our friends exponential of linear or angular momentum. We haven't talked about Hamiltonian. We haven't even discussed what it means to be a symmetry. Okay? You realize I haven't discussed any symmetry really of a physical problem. So I now discuss Hamiltonians. So we just make here a note saying that the rotation around theta n, okay, is represented by the exponential of angular momentum. Okay. If I have a certain Hamiltonian, okay, whatever, for instance, p square, which means minus h bar square, the Laplacian over 2m plus a certain potential, for instance, okay, just to give you some example, a particle in 3D. So this would be p square over 2m plus Vx. Now, to indicate that I'm using the coordinates x in here and in here, I will indicate it like that. Because I can make transformation of the coordinates, and if I transform the coordinates, this function changes, and the momentum also changes, okay? Because in general, I mix x, y, and z, and I have to take the new derivatives in the new variables. For instance, if I change variable to spherical coordinate, you realize how different is the Laplacian look, okay? But I'm not talking about this change of coordinates. I'm talking about the transformation t, which we have discussed before. So I will try to do things like tx equal to x prime, where t can be any rotor translation. All right. We will illustrate this with examples in a second. But for the time being, let me just give you a definition. If the Hamiltonian in the new variables, so I would write it h x prime, is exactly identical to the Hamiltonian in the old variables, I will say that t is a symmetry of h. Okay? Now I'm giving you a definition. But you realize that if a certain t is a symmetry and another t is also a symmetry, the product of the two is also a symmetry. Okay? So if you define as g of h, depending on the Hamiltonian, the set of all the t such that t is a symmetry of h, in other words, h in the variables x prime equal to tx is equal to h in the variable x, okay? Then this object form a group, and this is called invariance group of h, or symmetry group of h, okay? Now, here you have a name. Okay. It depends on the Hamiltonian, okay? because all possible rotor translations do not necessarily fulfill this thing, okay? There might not be symmetries. But if you find symmetries, they certainly form a group, a subgroup of all possible transformations, okay? Now, let me just stress this piece for a second. You realize that if I change variable from, for instance, x to x prime equal to x plus ax, y prime equal to x, y plus ay, and z prime equal to z plus ez, in other words, if I just do a translation, then the derivatives don't change, right? Doesn't matter if you, the derivatives are exactly the same for x, y, and z. In other words, the new momentum, okay, in the new variables square is exactly identical, okay? So if you do a translation, p square doesn't care. After all, p is the generator of translation, so it is absolutely inert to translations. All right. However, if you do a translation, this changes sometimes, very often, in fact. In fact, for most potentials, translations are not good. So suppose that this was just a square well, okay, between, say, minus a and a. So this is v infinity of x, okay, this function here. So it is equal to infinite inside, outside, and 0 here in a region between minus a and a. Now you realize immediately that, for instance, v infinity of x prime, where x prime is equal to x plus a, is v infinity of x plus, well, let's call this L, okay? Not to confuse it with the translation. This is a different function, okay? So is v, for instance, in x, suppose that you translate by twice L in x equals 0. Now this is equal to infinity rather than 0, okay? So it's just, it's this function translated, but it's not the same function, okay? So this is different from v infinity of x. Okay, so the Hamiltonian in the new variables, which would read p1 square over 2m plus v infinity of x prime, is different, definitely, from the Hamiltonian in the old variables, which would be this. Okay? Because simply the potential is not invariant by translation. This is very general, in fact. Any potential essentially breaks translation, unless it's flat, totally flat. Okay? So the only thing that admits translations as a symmetry is essentially the free particle, no potential. Okay, for a single particle at least. If I have proton and electron, on the contrary, the potential depends on the difference between the two coordinates. If you translate everything, the potential is the same. And so the whole system, proton-electron, is invariant by translation. And in fact, the center of mass is a very simple thing in that case. It moves by plane waves. Okay? So translation is a good symmetry for that case. But for the hydrogen, where you think of the relative motion only, no. Okay? So only if you allow both to move. Okay, so essentially don't think too much about translations because they are not so important in many of the problems we will find. They are again important, obviously, in solid state because there are some translations that are good symmetries. Translation by a lattice point, okay, of your crystal. Those translations are still good symmetries. And in fact, you can use them to simplify the solution of the problem by the well-known bend theory, block theorem, and so on. Okay? That follows from the symmetry Hamiltonian, of the Hamiltonian under discrete translations, okay? Not whole translation, but only a discrete set of translations. Okay. Now, let us think about examples for rotations. No, first of all, let us again look at the momentum. If I rotate something, for instance, the transformation I did before, so a rotation around z, cos theta, minus sine theta, cos theta, 0, 0, 1, 0, 0, x, y, and z. Now it takes quite a little exercise to realize that the same rotation will connect the gradient in the two coordinates, okay? So if here I have a certain r, I will have the same r here, okay? So please try to verify this. It's a very simple exercise which tells you the following thing. The momenta, because here apart from a minus IH bar, this is the momentum, the momenta transform in exactly the same way as the coordinates under rotation, which is a reasonable. You expect it, right? If you rotate something, the vector rotates in this way, and the momenta also rotate. They do it as operators, not only as classical images in your mind, okay? They are exactly the same rotated operator. But now you realize very simply that if I consider p square, okay, the Laplacian, this is now in the new system is p prime, p prime. But each p is the rotation of the old p. But this is a scalar product, okay? So it must not change. You can prove it very simply that this is exactly equal to p dot p, okay? So rotations do not change the Laplacian, in other words, okay? The sum of the three second derivatives would not change by a simple rotation. All right. This means that any time here I have, for instance, something that doesn't change by rotation, so for instance, something that depends only on the distance from the origin, okay, then the rotations leave the Hamiltonian invariant, okay? So for a potential like this, the so-called central potentials, the group of T such that T is a symmetry of the Hamiltonian is equal to the group of all rotations, okay? So group of rotations, okay? Is this clear? In fact, it's even improper rotation are fine, because if you change x into minus x, then p, you realize, changes it to minus p, but p squared also doesn't change. And this, obviously, doesn't change, because it depends only on the length of x, not minus x would be the same, okay? So all rotations are indeed belonging to the invariance group of this object, okay? Is it clear? Okay, now, there are examples that are in between. For instance, suppose that you have the potential in two or in three dimensions is not fully invariant. For instance, let me draw it like this. This is x and y. This is z. The potential is essentially a two-dimensional square well. Okay, so it's infinite all around here, and there's zero inside. Okay. You could think of this also in three dimensions. It would be a cube where you have zero potential and infinite outside. Now, obviously, if you rotate by an arbitrary rotation, the potential is not the same. But if you rotate by pi over 2 or minus pi over 2 or pi, or by nothing, identity, you have four operations that form a group. It's a finite group, not an infinite group, but it's a group. And it's a group of invariants of this Hamiltonian, okay? And by knowing a lot about the group, you would conclude about certain properties of the degeneracy of the eigenvalues. Okay? But this is not what I'm going to tell you. There is a whole chapter of, if you want, quantum mechanics that has to do with how to infer from the property of the group the properties of the possible degeneracies of the Hamiltonian. Now, let me prove the important theorem of this game, which is the following. So let me summarize. We have introduced the T, the operators, the operations. Then we have carried over them on the functions, and we realized that they are represented by certain unitary operators in general, exponential of P or L. Or, then we said all those T operations in space that leave the Hamiltonian invariant form a group. And now I close kind of the circle to show you the following thing. If I have this GH invariance group, and I consider all the PT, okay? So for each T that is a symmetry, I consider the associated P in the functions, okay? So T belongs to the invariance group of the Hamiltonian, and I consider all the P of T that I can construct. Now, you can prove two things. So this is a kind of theorem. The first is that this is a group of unitary operators that is, for the mathematician, they would tell you is isomorphic to GH, okay? Doesn't mean, I mean, you can forget about the isomorphic. Essentially, you realize PT just are clone of the T. They do the same things just on the functions rather than on the points, okay? In this sense, they are isomorphic, okay? The fact that they are a group is a very simple property because this is a group, and we said that if you can compose things. So you can realize very easily that indeed, if two operations belong to this, then the corresponding two can be composed, and they still are associated to a symmetry of the Hamiltonian. The fact that they are unitary, we proved it in general. They must be unitary. So this is not what I really wanted to stress. The important point is that all those PT commutes with the Hamiltonian. Okay? So this is the really important part of this theorem. So to summarize, if you construct all the symmetries in space, which, given the Hamiltonian, leave it invariant, then all the PT, which are associated with those T, computes with the Hamiltonian. Let us show this. It takes not long, and it's a very quite simple proof. So suppose that I have some Hamiltonian, say in the variable x, and generally speaking, applied to some function, okay? The result will be a new function, okay? Because the Hamiltonian will have some derivatives and things. Let me call this new function phi of x, okay? It's the application of h to psi. All right. Now, this thing here means that PT h minus hpt is just the same, is just 0. So the two things are just the same. Let us see what they do on a generic function, okay? So first I do PT h applied to some function psi of x. H here means it acts in variables x. It means that after acting, I have now a function phi of x, and pt does what? It's the same function calculated at t to the minus 1 x. Okay? But phi t to the minus 1 of x is what? Is the Hamiltonian in the variable t to the minus 1 x applied to the function psi in the variable t to the minus 1 of x. Okay? I simply read from here. All right? Good. Now I calculate the opposite. H applied to pt, psi of x. This is nothing but h is now the Hamiltonian in the x variable, the original one. Okay? Now this has to be applied to the function that is obtained by applying pt to psi, which is psi t to the minus 1 of x. You see that the two sides of these things, they differ because this function is the same, but the two Hamiltonians are h of x and h in the variables t to the minus 1 of x. But you realize that if t is a symmetry of the Hamiltonian, these two objects are just the same. Okay? Because we said let t be any operation such that h x prime is equal to h of x. Okay? All right? So you see immediately that these two things get to the same result, which means that they commute. All right? This is very important. Okay? So once you discover symmetries, you know that there are associated operators on the functions that commute. And commutation is very, very, very important because of a theorem that last time I just told you. This time I try to sketch you a little bit more. If I have two operators that commute, so suppose that I have a first Hermitian operator, A, you know that I can diagonalize it with the basis of eigenfunction psi phi A with a, say, certain eigenvalue A. Now, A might be either non-degenerate or degenerate. If it is degenerate, then here in principle I might have an extra index, okay, I, which spans from 1 to a certain degeneracy of the eigenvalue A, and all of them have the same eigenvalue. All right? So if I represent this in the as a matrix, you know that once I have a basis, I can associate to any operator a matrix, in general infinite. How do I do it? I have this operator. I calculate the matrix phi A I, phi A prime J. Okay? So in general, this will become an infinite matrix. Okay? But if these are eigenstates of A, the matrix is diagonal. Okay? So for instance, we have a certain A for a certain number of times, the A in here in the diagonal and 0 everywhere. Then another A, A prime, say, with a certain degeneracy d A prime, and all zeros, and so forth. They are blocks, okay, of a certain dimension, depending on the degeneracy of the thing. Okay? This is for any Hermitian operator. Now, suppose that you have a second operator, B. In principle, I could do a similar construction for B. However, generally speaking, the basis I construct for B has nothing to do with the basis I construct for A. Okay? So if I represent the two operators in the same basis, for instance, in this one, A might be perfectly diagonal, B might be totally scrambled, okay, totally full of numbers. Question is, can I find perhaps a common basis for both? A gentle basis on which both are diagonal, okay? So common eigenstates of both, okay? The answer is yes, if A and B commute, okay? So A and B commuting guarantees that I can form a basis which is common to both, in the sense that on that basis they are both perfectly diagonal. Okay? So in some sense, in this sought kind of basis, I would have, oops, I used the wrong thing. I will have certain elements phi a b such that a will give me just the eigenvalue a, and b will also be such that this is an eigenstate with a certain eigenvalue b. Okay? So this object is a common basis to both. You realize? What is the idea behind this? It's not difficult, okay? But I don't want to insist on a very formal mathematical proof. I just want to appeal to your reasoning to argue that it must be so. And the proof is not complicated. Let's see. Suppose that I restrict my attention to this set of this subspace of the Hilbert space. Okay, so they are vectors phi, which are somehow superpositions. Okay, with I going from 1 to the degeneracy dA of certain coefficients, let's call them alpha I, times the state phi ai, okay? Where A is fixed, okay? So I mix this thing in whatever way I want, all right? Now you realize that it really doesn't matter. If these are all eigenstates with the same eigenvalue A, whatever mix, I can take dA other mixture, okay? I can rotate those vectors in any possible way, and the representation for A would be identical, still diagonal, okay? Because this is like having the unit operator, okay? Doesn't matter what basis you take, it's still the same. This is very, very simple to understand, okay? So I can always construct combination of this, and it doesn't change, certainly, the structure of this matrix. On the other hand, let us see what happens to, let me calculate B applied to a state phi. Now, I want to show that if this state is in this piece of the Hilbert space, so it's a combination of this eigenstates that suppose I have chosen at the beginning, okay, phi a1, phi a dA, okay? I diagonalize A, and the program, for instance, gave me some vectors, and there they are. Not particularly adapted to B. They don't know anything about B, okay? Now, suppose that I form any combination, and I try to calculate B. I want to show you that this object is still in the same subspace. How can I show this to you? Let me apply A to it. Well, since A and B commute, I can also rewrite this as A phi. But this, being a combination of eigenstates with the same eigenvalue A, is just equal to A times phi, just the eigenvalue, a number, which I can take out. So this is equal to A B phi. Okay? So you realize what this is telling me. This is telling me that this vector is still an eigenvector of A with the same eigenvalue A, because they commute. And this is important because it's telling you that if I take any vector in here and I operate with B, I don't leave the subspace. I'm still there, okay? So if I represent in the same basis, which is not a smart basis, as I said, it knows nothing about B, but if I represent B, in that little thing, I'm sure I have numbers here, but only here. Okay? I don't leave that subspace. Here, there must be zeros. Similar for here, the second subspace. In general, okay, I will have numbers wherever here, but not outside, because you are guaranteed that they stay into the same subspace. They leave that subspace invariant. Okay? In particular, you realize that if this operator is non-degenerate, you immediately conclude that this is already diagonal. Okay? You have to do nothing. Okay? For a non-degenerate eigenvalue, B is already good. So it's happy with the same state. Okay? In general, if there is degeneracy, for instance, at least two vectors, you are not guaranteed that they are exactly eigenstates. But you know that applying B, you just mix them without exiting. But now you realize that you can refine your basis in the following way. Take new combinations here in this subspace. You can form dA new combinations, which diagonalize B in this restricted subspace. Okay? You can always do, because this is now an operator that is Hermitian in this restricted subspace. And you can always find appropriate combinations of the basis vectors that make this diagonal. But these new combinations, A doesn't care. It's still diagonal, because it's, within the same subspace. And I told you that no matter how I combine this vector, these are still eigenvectors with the same A. Okay? So these new rotations that I do there diagonalizes B without affecting A. That's the crucial point. All right? So in some sense, you realize that you can progressively refine your basis to diagonalize even the second operator. Because the second operator is very mild, is just doing some business in the local subspace, not going out. Okay? And you can realize that if I have three operators, I can proceed in the same way and successively construct other rotations that are common eigenstates in the end of all the operators. Okay? So the commuting operators, in some sense, have this very, very important property that you can find eigenstates that satisfy both or even more at the same time. When we will do next time the concept of measurement in quantum mechanics, we will also understand that this is deeply related to the fact that if you measure in the opposite way the two quantities associated with the operator, you don't really destroy the information of the previous measurement. We will do it next time. For the time being, the mathematical implication of the commutation is just this. And now you realize that, oops, we're kind of late, but let me finish with a couple of comments. We have already encountered this fact. First of all, let's go back to our hydrogen atom. Hydrogen atom, H, P squared over 2m. In fact, any central potential, P of r, which commutes with, which is invariant under rotations, okay? So GH is the group of all rotations. All right. Now I said the group of all rotations, for instance, any rotation like e to the minus I theta n over h bar dot L. This is the P corresponding, the P of t. This must commute with the Hamiltonian because this is invariant. All right? So I know that this object equal to this. Now, it takes very little to realize that this, since this is true for any theta, then it must be true in particular even for n dot L. So the angular momentum projected around n should also commute with h. Okay? Why is that? Well, very simple. Usual trick. Take the derivative with respect to theta, and then put theta equal to 0 at the end. Now, the derivative brings down here this object, okay? And then you take theta equals 0, means that the exponential disappears, becomes 1. So you bring down exactly this object apart from minus I h bar, which is not important. In this case, you bring down here the operator, not here, okay? Here, you put theta equal to 0, so you again have the same operator there, okay? So you see that this must be true, if this is true for any theta. But also, I'm telling you that this is true for any n, okay? So it means that really Lx commutes with h, Ly commutes with h, and Lz commutes with h, okay? In other words, h must commute with the full angular momentum, okay? Obviously, this implies that h commutes also with L square. Okay, so very simple properties to show. Now, unfortunately, L square itself does not, L square commutes with Lx, Ly, and Lz, but Ly and Lz, for instance, do not commute. So if you want to fish out what are the maximum number of commuting operators, you can certainly put h first in the list, L square second, certainly, Lz commutes with that and commutes with that, and that's it, okay? So you have these three operators, okay, which form a set, in fact, the maximal set of commuting operators that you can extract in this business. To be honest, in the hydrogen case, there is this also lens vector, but forget about this. If it is a central potential, that's basically it. Neglecting spin, neglecting spin. Huh? The? I am not taking dilatation in anything, because the length has, I mean, they change in a non-trivial way energies in this problem, okay? I'm just taking affine operations like rotations and translations, okay? Change of scale of length is a different business, okay? It's not symmetries of this type. Okay. Is this clear to everybody? Okay. And we, in fact, already constructed common eigenfunctions to this, this, and this, because we wrote the eigenfunction of this as radial functions, okay, times the spherical harmonics, and the radial function depended on k and l. Okay? So these are eigenfunctions of L square, Lz, and h. Okay? And indeed, by using this, we were able to reduce the problem to a one-dimensional problem. Okay? So without really mentioning it explicitly, we heavily use symmetry to solve the problem. Okay? Well, I think I have to stop here. Another examples that I could give, but maybe I start next time with that, is parity. Okay, parity is also there in many cases we have seen. For instance, the harmonic oscillator is even under parity. Okay, if you invert x into minus x, inversion is certainly respected. P square is even, and therefore the harmonic oscillator should commute with the operator P, which represent the inversion, okay? Which means that I should be able to construct a common basis of eigenvectors of harmonic oscillator and parity. Now, I should warn you, however, that doesn't mean that the eigenstates are even, because the parity operator admits two types of eigenvectors, the even and the odd. The odd are as good as the others, okay? They are not bad because the Hamiltonian is even, okay? The fact that there is parity, so the Hamiltonian is even, guarantees that this must commute with the parity, which means that I can construct common eigenstates. But the eigenstates themselves can be even or odd, all right? Okay, and there are certain consequences of these things which are sometimes very elementary and, however, very useful. Like, for instance, which matrix elements are expected to be 0 or not. These are called selection rules, okay? Selection rules. Sometimes, without really calculating a certain integral, so a certain operator between two states, you can tell me if that integral will be 0 or not, depending on the symmetry properties of the operator and the states, okay? We'll do an example next time. And this is useful when you do, for instance, perturbative calculations. You know if certain states will not contribute from the start without really calculating integrals, okay? All right, so I think we will reconvene here tomorrow to talk about measurement. What does it mean to measure in quantum mechanics? Okay, see you tomorrow.